temperature. So the rates of most chemical reactions increase as the temperature rises. So as the arrow for temperature goes up, the arrow for rate goes up. The rate of the reaction goes faster. This is generally because of what's called the collision model. And the collision model comes from the kinetic molecular theory, which we learned in Chapter 10. It says that all molecules are in constant motion and constantly slamming into each other. And if we raise the temperature, well, then we have faster atom motion, and then we have more collisions between those molecules. When there's more collisions, well, there's more chances for it to react. Now, that's not the only factor that decides whether a reaction will take place. And there's a second piece, and a third as well. This second one's called the orientation factor. And this one just means the way the particles collide. And they have to collide in the correct orientation for them to react. There's even a little diagram right here where they show this is the correct or the incorrect orientation, where these molecules might bounce together and then nothing happens, or this reaction happens, and then down here they bounce together, and this reaction they just stay the same because they didn't have the correct orientation to react. The third factor that makes a difference is one we looked at last video, and that is the activation energy. So it takes a minimum amount of energy to initiate the chemical reaction. So we drew these energy profile diagrams last video, and remember that energy right here needed to initiate the chemical reaction is called the activation energy, and it's from the beginning to the tippy top of the hill as the reaction progresses. By the way, this one would be endo or exothermic? Which one? Here's the beginning, here's the end. Oh yeah, it goes up, so it would be endothermic. Very good. So what can we do to lower this activation energy hill to make reactions go faster? Well, we'll learn in the next video there's something called a catalyst that can go and offer an alternative pathway for a reaction to happen, and it's one way to speed up a chemical reaction without using up something in the reaction. And that's one of the beauties of a catalyst that we'll learn in the next video, is that it can speed up the reaction without being consumed itself. So lastly in this, we want to look at a fraction of molecules graph. And I'm going to move this paper right here, and I'm going to pull it up on full color in our textbook right here. And the fraction of molecules graph shows kinetic energy on the horizontal axis right here. And then it shows the fraction of molecules with enough energy to react. And you'll notice that there's two different colors to this graph right here, and so if you've got different colored pens or pencils, you might want to use them. The first one that's a little bit taller right here, I believe is in a blue type color, and it comes down here, and then it crosses this little dashed line right here, and then they shade this area in, I believe, in blue. This line right here shows you the minimum energy needed to react. And so this is actually the E sub A, the energy of activation. So once you pass that amount of activation energy, then it'll react. And so for this amount of stuff, that would be the area underneath this curve right here, this area right here would be the fraction of molecules that can go ahead and react. Now you can shift this fraction of molecules to the right. You'll still have the same amount, but now more molecules are over in this area right here because it's from here all the way down to the bottom. And so if you calculus people out here, what do you call the calculation that's used, or the calculus operation that's used to calculate the area under the curve? That is your integral. Exactly right. And so you would have a larger population or a larger fraction of molecules if you had the temperature that is higher right here, and this is the lower temperature right here. And this larger amount happens because you shift the amount of molecules to the right, giving more of them more activation energy. So for you advanced folks, if you want to learn more about this, you'll want to look on this page in your textbook. It happens to be 596 in the 13th edition, but might change in the future. And there's an equation that allows you to find this activation energy. It's called the Arrhenius Equation, and it's used to calculate E sub A by making a plot of a graph of, well, something that is a constant, and you take the natural log of it, and then on the horizontal axis you graph 1 over temperature, and you find the slope of that line to find E sub A. Here is the Arrhenius equation right here for those of you that are interested. Good luck with your activation energy, collision models, and orientation factors, and knowing that higher temperature means faster rate.